Welcome everyone. In this video we are going to calculate Earth's escape velocity. Now in my previous video I described and derived the formula for escape velocity, so if you haven't seen that one, please go ahead and do so. It is on the from the cards right now. You can do that from the cards right now. So besides that, I still want to give a definition for escape velocity. Now we represent escape velocity with v and a subscript of e, standing for escape. And this is equal to the square root of 2 times g times m, some mass, divided by r, some distance. Now, for our case, this capital M is going to be the mass of the Earth, and this r, this capital R, is going to be the radius of our Earth. Okay? And as I said, I derived this formula. If this doesn't make sense to you, I really encourage you to go ahead and watch the derivation from the cards. But enough said, let's just calculate a value for Earth, okay? And the values that I will be using for G, M, and R, those values will be coming from Britannica's website. You can find the links to them as well from the descriptions part. So enough said, let me substitute. We have 2. And for G, we're going to have, for G, our value is, let me check, it is 6.6743 times 10 to the power of negative 11. Then we have the unit. It is quite important that we care about units. We have meters cubed, kilograms raised to the power of negative 1. So we have meters cubed per kilogram and then per square seconds. Okay. Now this was only the substitution for G. Now what about M, the mass of the Earth? The mass of the Earth, it turns out, is equal to 5.972 times 10 to the power of 24 kilograms. This is a huge mass. This is incredibly huge, and it should make sense to you that it is a big number because the Earth is huge. And then we have r, the radius of the Earth. Now, you might know that the Earth is not a perfect sphere, so the radius varies from location to location on its surface. So which radius value should we use? Well, I am going to use the equatorial radius. And if you want to know a little bit geography, I can tell you that equatorial radius is the greatest radius. For example, polar radius is less than it. So Earth is a little bit greater, bigger when we are interested in the equatorial radius. It is just how it is shaped. So if we plug in the value for the equatorial radius, it turns out that value is 378.14 times 10 to the power of 3 meters. And of course we have the square root as well. Now I will calculate the value of this, and I actually did. I will write it. I am looking at my calculator right now. But let's just analyze the units together, all right? Because if the units don't match a unit of velocity, we got it all wrong. We will start over. We must have made a mistake if the units don't match. If they match, we still could have made a mistake, but we could have got the correct answer as well. We can tell actually. So if you look at the units, we see that 1 meter cancels here with the cube here. So we have meters squared. And then a kilogram here cancels with the kilograms raised to the power of negative 1. And we have only seconds here, and it is seconds raised to the power of negative 2. So we have inside the square root meters squared divided by seconds squared. So when we take the square root of it, we get meters per second, which is actually a unit for velocity. So this is great. We didn't do a dimensional mistake. We can be sure about that at least. And this value gives you, as I said, I calculated this, and I challenge you, I encourage you to calculate this yourself as well. Maybe I made a typo, I made an error, could be, right? Never trust anyone if you can check something. So this is going to be 11,179.715079 meters per second, and we should of course round our answer, and I'm just going to round it. I'm going to be lazy. I will just call it 11 kilometers per second, right? Because kilo means 10 to the power of 3. And as you can see, we are in that order of magnitude. And you can appreciate the fact, I think, this is a huge velocity. This is how fast you should fire a rocket from the surface of the Earth so that it escapes the orbit. Otherwise, it is going to fall back. So you can't have it explore the rest of the solar system if you fire with a velocity less than this. And of course, you would need to account for air friction and other planets, so this value would vary, right? What would air friction do? Well, it would increase this value. And we can't really tell what the other planets effect will do on this velocity. It might increase it, might decrease it, and it might depend on the time of the year. The effect might vary, but as I said, friction would tend to increase this value. But this is a theoretical value that we get for the escape velocity of the Earth. You can do similar calculations for other planets and Sun perhaps. Anyways, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.